first we begin with very general issues about quantum gravity and the conceptual setting for quantum gravity. And then I will focus on one of the approaches that I work on, which is loop quantum gravity as a whole. And then in the third part, I will come to the one of the themes of the conference, as has been emphasized this morning, which is marrying experiments and theory. So here I'll talk about a bridge between theory and observations using the very early universe. Philip mentioned that early universe is one of the places where we could actually have observable effects, and we'll see that. And then finally, a summary and a broad perspective. So this is just a general historical and conceptual setting. Quantum mechanics is arguably the most successful area of fundamental science. And general relativity is the best theory of gravity we have, and it has surpassed many stringent tests. Quantum gravity is the theory that will unify the principles of these two, and that is the theory we are looking for. This unification has been widely regarded as the most outstanding conceptual issue in fundamental physics. But this is not something that is new, in the sense that that is something that we have known already from Einstein already in 1916. In the paper in which Einstein published his quadruple formula, the first formula about first paper on gravitational waves, in the weak field approximation, he said, nevertheless, due to inner atomic movements of electrons, atoms would have to radiate not only electromagnetic, but also gravitational energy, if only in tiny amounts. As this is hardly true in nature, it appears that quantum theory would have to modify not only Maxwellian electrodynamics, but also the new theory of gravitation, which is, of course, general relativity. Now, the point is that this was in 1916, more than 100 years ago, and physics has advanced tremendously over the last century, but the problem is still open. So why? Now, the obvious answer that we hear from many people is, well, this is sort of difficult. It's just like general relativity, had predictions, but really strong field tests really came from gravitational waves 100 years after the theory was actually put forward. And so our problem is is that there is no experimental data with direct ramifications on the quantum nature of gravity. Well, but if this is the case, if this really is the only reason, then in fact, there should be a plethora of good theories, right? Because without experimental constraints, it's like a theory's heaven. You can churn out a theory a day, right? So, but we don't have even a single consistent theory. So then this cannot be the whole problem. And I believe, like many of us, I'm a representative of a large community which believes that, in fact, in general relativity, gravity is encoded in the very geometry of space-time. Most spectacular predictions of the theory, the Big Bang, black holes, and gravitational waves, emerge from this encoding of gravitational field in the geometry of space-time. And this suggests that if we want to have quantum gravity, then geometry itself must become quantum mechanical. Therefore, there is going to be some fuzziness, there is going to be some probabilistic aspects about it. And the problem is, how do you do physics if you do not have a background space-time on which to work on, a sharp space-time to work on? And this is really, I think, the fundamental problem that we have up here. Namely, we need new concepts as well as novel mathematical tools. And basically, we are so used for centuries to tie ourselves down to a background space-time, and we have to lift that anchor and learn to sail the open seas. And it has taken us quite a while, but I think we have begun to make progress in this direction, as is illustrated in this conference in various approaches. And there are several voyages in progress. We already heard about string theory, loop quantum gravity, but we also have asymptotic safety, dynamical triangulations that Renata will talk about, Reggie calculus, causal sets that Steve Carlip will talk about, Euclidean quantum gravity, twistor theory of Roger Penrose's, and so on. And then there are these various other ideas that will be discussed later in this session about effective field theories. Both Donahue and Steve will talk about that. And so there are several voyages in progress up here. And I think concrete progress really is occurring. But however, because there are no direct experimental checks, these diverse approaches the starting points are rather different. And they are driven by intellectual prejudices about what the core issues are, what one should tackle first, and then maybe other things will take care of themselves. Well, this at first to people who are not in the forefront of science or doing these things, sounds very strange. Namely, the assertion, it seems almost shocking to non-experts, because isn't science meant to be objective? And how can it be that these things are driven by intellectual prejudices? And I think there is a very beautiful quote by C.N. Yang, which actually tells the story in a very succinct manner. Namely, that taste and style has so much to do with physics may sound strange at first. Since physics is supposed to deal objectively with physical universe. But physical universe has structure, and one's perception of this structure, one's partiality towards some characteristics and aversion to others are precisely the elements that make up one's taste. Thus, it is not surprising that taste and style are so important in scientific research. And so I think various people will talk about various approaches in which there is some taste involved, there is some belief involved as to what is more fundamental, that should be emphasized. Now, I would like to just give two illustrations of this taste and style. The first is from string theory, and the second is about loop quantum gravity that I'm going to discuss in a little bit of detail. And the string theory was developed by high energy theorists, and therefore, for them, unification of all interactions was, in the beginning at least, was a central goal. And this led to the introduction of supersymmetry, higher dimensions, negative cosmological constant in the very foundation of the theory. None of them were sort of known to be present in nature at that time, but it was felt that unification was pointing towards that direction, and therefore, this was a small price to pay to get there. And the point particles are replaced by extended objects, strings, membranes, and so on, and they then, therefore, provide an avenue towards an ultraviolet cutoff. By contrast, loop quantum gravity was developed by relativists. So their idea about what is more fundamental was quite different. Non-perturbative approaches and background independence is central. What do I mean by background independence? Well, we learned from Einstein that geometry encodes, space-time geometry encodes the gravitational field. There is no other metric there. There is no other space-time. The space-time metric is dynamical. It is like matter field, right? I mean, they're all interacting with each other. They're evolving, and so on. And so, therefore, we should not introduce a certain background around which we do perturbation, because that background is fictitious up here. And this led to the introduction of what is known as quantum Riemannian geometry. Basically, in general relativity, really had told us that we needed a new syntax to describe the classical world. And that syntax is provided by Riemannian geometry. And now the new syntax that is required is supposed to be provided by quantum Riemannian geometry. And therefore, because of geometry itself is quantum mechanical, it has an atomic structure, and that provides an ultraviolet cutoff up here. And the mainstream thrust in the two theories also have been therefore different. In string theory, this is a quote that is taken from an author, Casey Cole. She was a journalist at the Institute for Advanced Study in Princeton, and you can find it on the website of Princeton. It also appears in the Quantum magazine. It says, the title is The Strange Second Life of String Theory. String theory has so far failed to live up to its promise as a way to unite gravity and quantum mechanics. At the same time, it has blossomed into one of the most useful sets of tools in science. So even up to now, this hopes that one would actually find supersymmetry and higher evidence of higher dimensions and a negative cosmological constant, they have not been realized. And that is a part of the first part up here. But nonetheless, string theory has given us plethora of new techniques, and some of which we saw this morning, which actually suggested various ideas in pure mathematics, in QCD, and so on and so forth. And they have been very, very, very useful. So the current mainstream thrust is really, so they have been very, very successful. In loop quantum gravity, the focus continues on the long-standing quantum gravity problems taming problem of time. What do you mean by time? If, in fact, the space-time itself is quantum mechanical. The taming of the Big Bang singularity, the pre-inflationary dynamics, and large-scale anomalies in the quantum, in the cosmic microwave background, and finding correlation functions in a background-independent theory. So these are some of the things that people have been thinking about. Okay, so this is the first part, and now I would like to tell you about a brief introduction to loop quantum gravity as a whole. So, as I said, general relativity is founded on Einstein's outrageous idea that gravity is not a force, but it's a manifestation of curved space-time. Therefore, general relativity needed a new syntax, as I just mentioned, for all of classical physics, and that was provided by Riemannian geometry. In the loop quantum gravity community, then, the idea is that, in fact, because geometry is a physical entity, just like matter, and the two are related to each other by Einstein's equations, and because of that, it's also a dynamical entity, and it should also have an atomic structure, just like matter. And quantum gravity, therefore, needs a yet new syntax, and now, for all of known physics, and this syntax is provided by quantum Riemannian geometry, which is systematically developed by a very large number of researchers over the last 3 decades. The main thrusts are summarized in these pedagogical chapters in this book, Loop Quantum Gravity, in which leading young researchers actually wrote this, and this was a monograph in 100 years of general relativity. There's also, for students and so on, there's also an introductory outreach YouTube video, 75 minutes long, it's quite long, is the story of loop quantum gravity from Big Bang to black holes. So what are the main ideas? Loop quantum gravity, in loop quantum gravity, there is a precise and detailed mathematical framework that captures the nature of quantum geometry. It provides a syntax to describe how general relativity is modified at the tiniest scale, the Planck scale that we heard about this morning. The fundamental excitations of geometry, because geometry is a physical entity, so it is a quantum mechanical, there are fundamental excitations, and these are polymer-like, they are one-dimensional. Einstein's continuum arises only on coarse graining. Literally, the fabric of space is woven by a one-dimensional thread in a precise manner. And the analogy that I often like to give is that of a fabric. For example, my shirt up here. The shirt looks like a nice two-dimensional continuum, solid, but you just have to take a magnifying glass and look at it, and you will see that it is woven by one-dimensional threads. So the space-time continuum around us, the space continuum that we see, looks like continuum, but that is because it is crisscrossed by fundamental excitations at Planck scale that are so close together that, in fact, what happens is that it gives us an approximation, which is an extremely good approximation of continuum. But at a fundamental level, however, it has an atomic structure and these one-dimensional excitations. And here is a picture in loop quantum gravity of, for example, a black hole. This is the surface of a black hole. The black hole is punctured by these fundamental excitations, and each of these excitations deposits a quantum of area, and the sum of those make up the area of the black hole. Therefore, for a macroscopic black hole, there is really huge, astronomically huge number of these intersections from the polymer geometry into the surface of the horizon. Observables such as geometrical observables, such as areas of physical surfaces. By physical surfaces, I mean area of this, for example, the sheet of paper. The sheet of paper is defined in an invariant manner as a surface of discontinuity of density. There is no density is equal to 0 here, density is not equal to 0, density is again equal to 0. So if you take such physical surfaces and calculate their areas, then the statement is that there is a precise operator corresponding to them, and these areas, the eigenvalues, they are quantized, exactly like the discrete energy level of atoms. There is a minimum non-zero value for this area, it is called area gap, and it is about 5 times Planck length squared, so about 10 to the minus 66 centimeters. And that turns out to play a key role in the definition of quantum curvature and quantum Einstein equations. And the presence of this minimum area is what regularizes the geometry, the dynamics, Einstein dynamics. So the area is quantized But this discreteness is sophisticated. It is not like I got one quantum, another quantum, equally spaced. But they actually crowd, like the spectrum of the hydrogen atom. They crowd, but in this case, the crowding is even exponential. So larger the area, the next eigenvalue is even closer to the previous one. Next one is even further closer, and so on. And that is why the continuum approximation works so well. So the discreteness is sophisticated, and area eigenvalues crowd exponentially. So here is a kind of a pictorial representation of the space-time continuum. It's like what happens in an impressionist painting. There really are dots, but from a distance, it looks like a continuum regular picture up here. So from loop quantum gravity perspective, space-time continuum of general relativity is an approximation which only emerges on coarse graining, and probing physics at scales much larger than Planck scale, we can have this approximation. Then we can ignore the atomic structure, like what we do when we look at a wall, and we say I have an impressionist painting up here. So some of the long-standing questions of quantum gravity, irrespective of the approach, have been the following. Quantum mechanics and general relativity led to profound paradigm changes in our understanding of the physical world, each in its own way. We had to learn to formulate meaningful questions before we could answer them. In each case, we had to rewire ourselves, so to say, to ask the right questions. Quantum gravity is expected to lead to even more profound paradigm shift, and therefore, we face deep conceptual quandaries. For example, how do you do physics if there is no space-time metric to anchor it? What is time, and how do you speak of dynamics or happenings? Are strong curvature singularities of general relativity naturally resolved by quantum gravity because of the quantum geometry effects? What really happened at the Big Bang, and what really happens inside the black holes? So these are some of the questions, some of the fundamental deep questions, some illustrative questions that I'm sort of taking up. And answers from loop quantum gravity are the following. How do you do physics if there is no space-time metric to anchor it? Well, matter fields and geometry are both quantum mechanical at birth. Matter propagates not on a fixed space-time geometry like Einstein, but on a wave function of these geometries, representing a probability distribution of such geometries. This, you can get rid of the wave function, and you can just talk about histories, if you like. And the statement is that there is not one history, but there is a whole bunch of histories, and you have to sum all those histories up here. And the analogy is like that of electrons in a laser beam. If I have a laser beam, like this laser beam, and if I put the electron in there, then to the first approximation, the electron just feels a classical field, which is really the expectation value of the Maxwell field operator. But then to the next approximation, it also feels the quantum fluctuations, because the electromagnetic field is a coherent superposition of photons, and therefore there are uncertainties, and therefore there are fluctuations in the electric and magnetic fields, and the electron would feel it. And the idea is similar here, that to the first approximation, you would see just a classical geometry, but when the curvature is very strong, or if you have very sensitive instruments, you should be able to see these fluctuations, effect of these fluctuations on matter as well. What is time, and how do you speak of dynamics and happenings? Well, dynamics is done in a relational way, like Leibniz. So there is no absolute clock, but rather the evolution is really relational. So for example, you can choose one matter field or an attribute of space-time geometry, and you can use that as a clock with respect to which other attributes of space-time geometry and matter fields evolve. So really a relational clock, and particularly in cosmology. There is no grandfather clock in the background. There was no concept of a year before Earth started orbiting around the sun, for example. But we can have some relational dynamics still. So example of happening is, for example, creation and annihilation of new nodes or chunks or quanta of volume. This is what happens when the universe actually is expanding. New nodes in the geometry of space-time are being created, and these are discrete quanta of volume. Are the curvature singularities of general relativity naturally resolved by quantum gravity? In all cosmological and black hole models considered so far, strong curvature singularities are tamed in loop quantum gravity, so physics does not stop abruptly as in general relativity. Loop quantum gravity equations continue to be well-defined and lead to new predictions. So this is the second part. And this, what I have to try to do in the first part is really a global picture about why the problem is still open and why different approaches are going on. For a long time, I sort of emphasized that this variety is essential. Should not have the attitude that one approach is correct and everything else is wrong. And cross-fertilization of ideas is where the true progress will occur. And that is why this institute, for example, this society, quantum gravity society, is going to have a deep impact by bringing it together people thinking along different lines up here. So now, what I would like to do is to, and then in the second part, I gave a brief introduction to loop quantum gravity. And now I'm going to talk about a bridge between theory and observations. And again, because I got only so much time, I'm just again going to focus on loop quantum gravity and give an example about this. So loop quantum gravity and the early universe. Now, there is a standard model of cosmology that was given to us by Lemaitre, Friedman, Lemaitre, Robertson, Walker. It's a solution of Einstein's equation with matter fields which are homogeneous. So there is no special place in the universe, and which are isotropic. So there is no preferred direction in the universe. And these solutions lead us together Einstein's equations. They tell us that so this spacetimes capture the large-scale structure of the expanding universe. However, so this is a pictorial diagram. Time is running up here, and the cross-sections here are like space, and space is expanding, as you can see up here. But if you go backward, then of course the space contracts, and then finally we got this Big Bang. And this is the Big Bang at which everything, including space-time, is born in general relativity. However, already in 1945 edition of Meaning of Relativity, Einstein cautioned against attributing fundamental significance to the Big Bang. He said, one may not assume the validity of field equations, Einstein's equations, at very high density of field, at very high curvature, and matter density. So one should not assume the validity of Einstein's equation at very high curvature and matter density, and one may not conclude that the beginning of the expansion should be a singularity in a mathematical sense. So, I mean, how could this singularity then be avoided? What quantum effects can happen? Well, there can be new forces of quantum mechanical origin. Now, by now, Einstein's conclusion is widely accepted. The prediction of the Big Bang requires one to use general relativity equations beyond the domain of its applicability because they ignore quantum physics. In the backward time evolution, matter density and space-time curvature become enormous, and quantum physics become particularly important there. And these quantum effects are ignored by general relativity, and therefore singularities, like the Big Bang, are gates for physics beyond Einstein. Now, here is an example of a genuine quantum force, which is, I think, most of you know, which is neutron stars. They would not even exist in the classical world. They are like gigantic nuclei, so dense that a teaspoon of their matter weighs about more than 1 million tons. If the world were classical, such dense stars would collapse into a black hole under the gravitational attraction. But quantum mechanics intervenes and creates a new repulsive force, which has no analog in classical physics, the Fermi degeneracy pressure, that balances the gravitational attraction. And quantum mechanics stabilizes the neutron star if their mass is less than about 2 solar masses. So the same thing happens for geometry. So this is for matter, but the same thing happens for geometry in loop quantum cosmology. Quantum geometry of loop quantum gravity corrects Einstein's equations. So we don't have Einstein's equations all the way. They're corrected Einstein's equations. As we go back in time, these corrections create a brand new repulsive force in the Planck regime. This has nothing to do with matter. This really has to do with geometry itself. Because geometry itself is quantum mechanical, this is what happens. It's related to the fact that there is an area gap that I mentioned before. And when the matter densities are about 10 to the 90 times the nuclear densities, and the space-time curvature is about 10 to the 76 times the curvature of the horizon of a solar mass black hole, this is the Planck regime. And in that Planck regime, the quantum effects of geometry become important. I sometimes tease my friends and my colleagues in LIGO, saying that, well, you talk about very strong gravitational fields, black hole surfaces. But look here, in the early universe, the curvature is about 10 to the 76 times the curvature of the horizon of a solar mass black hole. So the statement then is that if the force is negligible until we reach this Planck regime, but then rises extremely rapidly and overwhelms the classical attraction and causes the universe to bounce. Once we are on the other side, when the curvature falls below that, again, classical general relativity becomes an extremely good approximation. So this is what one can see in detail in equations. So here is an artistic impression. The future branch up here is our universe. You go back in time, and then classically there will be a Big Bang. But here, actually, there is actually quantum bounce. The universe bounces because of this new repulsive force, and then we have a regular geometry, except that here, in this bridge up here, quantum mechanical effects are very, very important. All physical quantities remain finite at the bounce, and space-time curvature is large. It is about 62 times the Planck scale, but it is actually finite. Matter density has an absolute upper bound, and that is about 0.41 times Planck density, which is enormous, but it is finite. As the area gap goes to 0, this becomes infinite, as in general relativity. So really, the fact that we have got quantum geometry is really responsible for this bounce. Away from the Planck regime, when rho is much less than or equal to 10 to the minus 4, general relativity becomes a good approximation. And even at the onset of inflation, rho is only 10 to the minus 11 rho Planck. So therefore, in loop quantum gravity, has no problem with using, with inflationary people using classical general relativity during inflation. So long as we can at during inflation, we can safely use a classical continuous space-time. But not before. If you go back in time further, then the Planck curvature comes up, and these corrections become very important. The area gap of loop quantum gravity serves as the microscopic parameter that sets a scale for macroscopic observable. For example, the density of matter is given by 1 upon cube of the area gap. There is actually, this is something that came out first in loop quantum gravity, but this is not something that is now, I think it is widely accepted. There is this very short video, about 10 minutes maybe, in which 6 of us were interviewed, and all of us agreed that Big Bang is not an initial singularity, but a hot phase of the early universe, and say at the end of inflation. All the 6 people had different ideas, following different approaches, but this is the conclusion that was shared by everybody. Okay. So now, what about observations? It's fine. You've got a big bounce. There's no singularity. But could we ever test that? Could we ever actually have any observational evidence for that? So our information about the early universe come from CMB observations. And for the CMB observations, these are the cosmic microwave background observations. I'm plotting this thing, which is kind of seen many, many times. This is the L, and L is just spherical harmonic decomposition. So small L's means large angular scales, and large L's means small angular scales. So you're looking at the structure at small angular scales or large angular scales, and that is what is shown up here. And the point is that here, as you can see at this small angular scale, the standard inflationary predictions agree very well. But at the small L's or at the large angular scales, in fact, the observed power is consistently lower than that of the predicted by inflation. And furthermore, for this universe, the theoretical predictions for other observables, such as the lensing amplitude and odd parity BB power spectrum, these can be measured, and they would provide us with further tests of the standard model or some glimpses into quantum gravity regime up here. Now, can there be observable signatures of the big bounce? By and large, predictions of both the standard theory with Big Bang, standard inflation, and LQC with big bounce, they agree with observations. But now, in observations, there are some anomalous features. I already mentioned the power suppression. Here, so this is the thing that I had in the last slide, at this part up here. But there is another way to write this that makes it more vivid, and that was proposed by the WMAP people, particularly Spergel and various other collaborators, and also used now by Planck people. And that is looking at how much power there is in the observed radiation, the CMB, as a function of theta up here. And the statement is that as a function of theta, what we find is, so these are the angles up here. It should not be L here. This is the angle up here. And then what we find is that the actual power is really suppressed. If you go around 60 degrees and up here, then you can see that the actual power is very, very low, whereas the standard prediction is very high. This is C. The actual power is square of this. So in fact, the standard prediction for C squared is quite high compared to this. And this is called the power spectrum suppression anomaly. And there is another parameter called the lensing amplitude. And in standard inflationary scenarios or in standard data analysis, its value is taken to be 1. So deviations from 1 show that there is actually a problem. And here, the statement is that the observed value up here is really is outside the 1 sigma contour. In fact, if you just look at that lensing amplitude itself, then the problem is essentially 2 sigma problem with respect to the observations. So by and large, everything works very well, but there are these anomalies. Now, should we take these anomalies very seriously? Well, if there is only one anomaly, then probably not, because statistical significance is not very high. Our universe could be realized if you have simulations, then we look at some representatives, and it could be realized in 1 in 1,000 representatives or 5 in 1,000 representatives, and that is okay. But if you have 2 or more anomalies, then the universe is really, our universe corresponds only to 1 in a million. And that, I think, is considered to be reasonably serious. So this is what Planck paper said, both in 2015 or 16, 15, and as well as 2018. If anomalies have primordial origin, then their large-scale nature would suggest an explanation rooted in fundamental physics. Thus, it is worth exploring any models that might explain an anomaly, or even better, multiple anomalies naturally or with very few parameters. And what has happened in loop quantum gravity is the following, that the curvature is finite at a bounce. And because the curvature is finite at a bounce, the curvature radius provides a new quantum mechanical length scale, a new length scale which came from quantum gravity. And then the modes of this CMB, cosmic microwave background, whose physical wavelength is less than the radius of curvature, they don't experience curvature, while those whose wavelength is larger, they do. This is like by walking on the surface of Earth. I'm walking, Earth's surface is curved, I don't feel any curvature, because my step size is much smaller than the curvature or radius of Earth up here. On the other hand, if I fly, that length, that is like the wavelength, then you do feel curvature of Earth, and we have to take that into account. So that is what is happening, that loop quantum gravity, quantum geometry effects are providing a new length scale, and wavelengths larger than that, they do see curvature. So it is very interesting, because the new length scale came because of ultraviolet corrections, because of that is what resolved. The curvature is not infinite, but it's finite. On the other hand, their effects on perturbations is on the long wavelength modes up here. So there is a duality between ultraviolet, the ultraviolet, the small wavelength, small scale, and the infrared. And therefore, this is called the cosmic tango, and these results were written up in various magazines. And this cosmic tango is between the very small and the very large. The Big Bang singularity is resolved because of Planck scale corrections to Einstein's equations induced by quantum geometry. I'm just repeating what I said just a minute ago. New length scale, RB, that they create, this at the smallest length scales, they affect the longest wavelength mode we observe in CMB. Thus, there is a cosmic tango between the very small and the very large, and near the big bounds, that makes it possible for quantum gravity to lead to some effects which leave an observable imprint on the large-scale features of CMB without compromising success of standard inflation. So here are the standard inflation, the standard models, the standard cosmological model parameters. It's a 6-parameter model up here. And you can see that the difference between the two are almost negligible for 5 of the 6 parameters, But for us, one parameter, which is called the optical depth, sort of the epoch over which reionization was important, that changes, however, by about 10%. The others change by less than 4.4%. And now, in this optical length, optical depth would actually be measured. Tau would be measured, but more directly by upcoming missions, independent of the CMB, and thus there is a concrete bridge between theory and experiments. So this is the main point that I wanted to convey to you. These are illustrations. Yeah, I'm almost done. These are the illustrations. And the point up here is the following. I just want to end with a broad perspective on quantum gravity. Because the problem of quantum gravity has been with us so long, until recently, there was no obvious observational window to test these ideas. Leaders have often made appeals to aesthetics. For example, one finds quotes from eminent and thoughtful people like, there was, I think somebody mentioned in the talk today about Plabansky and the edge spaces and so on and so forth. So this is a quote, "It would have been a cruel God to have laid down such a pretty scheme, the edge space and heaven, and not have it mean something deep." Similarly, about string theory, there is a famous quote, "I just think too many nice things have happened in string theory for it all to be wrong. Humans do not understand it very well, but I just don't believe that there is some big cosmic conspiracy." Here one is talking about a cruel God. Here is a cosmic conspiracy that created this incredible thing that has nothing to do with the real world. So I just have, yeah. Good. So here is a reminder from Feynman. So these are the same things that I mentioned. Feynman says, it doesn't matter how beautiful your theory is. It doesn't matter how smart you are or what your name is. If it doesn't agree with experiment, it is wrong. And I think in quantum gravity, we really need to sort of have this. I mean, there's too much thing about just aesthetics are important to drive you to do something. But you should not, that is not the end of the road. That is kind of the beginning of the road or the middle of the road. And there are very famous examples from history. This is the last slide. Steady state cosmology. People thought aesthetically that was much, much better than Big Bang. Then John Wheeler had an idea that elementary particles really should be thought of as chemistry of geometry. It's a beautiful idea, but so far is not realized. Replacement of local quantum field theory by analytical properties of S matrix. This again was a very beautiful idea, but then there was a hiatus for a long time, and is now again being revived. So I don't mean to say that all ideas which have been put forward before are sort of incorrect, but on the other hand, they did not need to progress. And the last thing is atoms as knots in space-time. Now, this is something very interesting because this was really in the beginning of end of 19th century, when very famous people, including Lord Kelvin, Maxwell, thought that the most elegant way of describing atoms is as vortices in ether. And simple atom would be just a circle. Helium atom would be a trefoil knot. So there are knots in ether. And none of those things actually worked out. That gave rise to a beautiful theory of knots. Knot theory started because of this, because Kelvin pushed Tate, mathematician, to develop knot theory. But that doesn't mean that it has necessarily something to do with nature, and we should keep this in mind. Okay, so for students, I just want to leave this. There are a few references. Thank you very much.
Thank you very much, Abhay. I think we have time maybe for one question.
Yeah, we got 47 seconds of my 40 minutes.
So, right, Marcus, one question.
There's a challenge, the only question. I apologize for being in the lame question now, but that's the one I have. So thank you very much for this extremely beautiful overview. Since you said that loop quantum gravity could be possibly a solution to the anomaly in the large-scale CMB distribution, I was wondering on whether there exists a corrected plot that you showed
Oh,
on your
yeah.
on your
Yeah, we
page
do have.
22.
I removed it just because of this time, right? I mean,
Okay.
I prepared. Yes, there are corrected plots, and they are in the. I can give you the references, but anybody who wants to look at it, you can look on the archives, and it is actually called the Cosmic Tango. No, I don't know if it's. Yeah, what the detailed paper has a Cosmic Tango in it. It's kind of a year and a half old paper, so you can see that, and all the detailed plots of loop quantum gravity versus that, and how much improvement there is tabulated there.
Okay, thanks a lot. So I will look that up. Thank you.
Thank you. Yeah, so Steve, why don't you come up?
Does loop quantum gravity have anything to say about the Hubble tension that has been happening?
Yeah. So there is an idea because by Alejandro Perez around these lines, but it's not as detailedly developed as these other ideas that I'm talking about. But there is an idea, and you can look up Alejandro Perez about it. I myself am very not convinced by those arguments, in a sense that could be a beginning, but I don't think we are anywhere. I don't mean to say that what I presented is the end, but it is sufficiently detailed that one could take it seriously.
Thank you.